Propellers are crucial to engine life and optimum performance. The propeller is where the power meets the water, so it's important to choose the correct prop to unlock the engine's full potential and ensure customer satisfaction. To make the correct choice, you must first understand how propellers work. The blade is the part that actually moves the water. The blade is thickest at the hub and gets thinner as it gets closer to the blade tip. The blade area has two main functions. The blade back, which is the side closest to the boat, creates a low pressure area as the prop rotates. This low pressure helps pull the prop forward. The blade face, which is the side opposite the boat, creates high pressure as it rotates. This high pressure forces a stream of water, called a thrust cone, to the rear. The thrust cone pushes against the undisturbed water around the prop and moves the boat forward. The leading edge of the blade is the area that first makes contact and cuts through the water. The trailing edge of the blade is where the water leaves the prop to form the thrust cone. The center of the prop is called the hub. You'll find a number on the hub. This one says 14 3/4 by 17. The first number, 14 3/4, is the diameter of the prop, measured in inches at the tips of the blade. The second number, 17, is the pitch. Pitch is the distance the propeller would move in one revolution if it was cutting through a solid, such as gelatin. Of course, water isn't solid, and the propeller will slip a bit, but not as much as you might expect. A good engine prop combination will generally slip less than 10%, and maybe only a couple of percent. Lower pitch props create less forward travel with each revolution, which is helpful for big boats and heavy loads. Higher pitch props produce less low-speed pulling power, but more top-end speed. Let's clear up some poorly understood terms: ventilation and cavitation. Ventilation occurs when external gases, such as the engine's exhaust or surface air, get into the propeller's blade area. If the prop is pushing air, it isn't pushing as much water as it should, and this causes loss of thrust, an increase in engine RPM, and poor performance. Ventilation can be caused by running the prop too close to the surface, wrong trim angle, severe turns, large keels, fouled boat bottoms or lower units, hull protrusions such as transducers, or loss of the converging ring from aluminum props. Cavitation happens when rough or damaged areas on the prop disturb the smooth flow of water. As water flows around the damaged area, it's deflected away, increasing the speed of the water and creating a low-pressure area. This low pressure causes the water to boil and turn to vapor. These vapor bubbles move into the high-pressure area behind the blades. There, they collapse back into water, creating tiny high-speed impacts on the blade face. The end result is a pitted or eroded area on the propeller. Cavitation can also happen if the prop is loaded too heavily due to poor design or incorrect application. It can be prevented by making sure the prop is correct for the application and it's in good shape, no dings, dents, or other defects on the leading edges. Ventilation, on the other hand, can be a little trickier. To deal with this, on some props, the trailing edge is curled. This is called blade cup or cupping. The cupping forms a seal to help prevent bubbles on the low-pressure side of the blade from reaching the high-pressure side. By reducing ventilation, this lets us trim out farther. Cupping may allow you to raise the engine on the boat's transom to improve the boat's performance. The cupping may have the effect of adding as much as 2 inches of pitch to the prop. This can reduce engine speed by as much as 150 to 300 RPM at full throttle. Most aluminum props have a converging ring, and some stainless steel props have a diverging ring. These rings reduce exhaust back pressure, and they prevent exhaust gases from getting into the propeller blade area. As the gear case moves through the water, the water velocity around the gear case increases. This creates a low-pressure area around the gear case and prop hub. The engine's exhaust tries to migrate to this low-pressure area, where it can reach the blade area. The converging or diverging rings help form a seal between the exhaust and the blade's working area. At planing speeds, the ring will help seal the water as it leaves the prop, forming a strong low-pressure area behind the prop. This will draw exhaust from the engine and reduce exhaust back pressure, which is crucial for good performance and powerhead durability. Another design characteristic of propellers is rake, which is the angle of the prop blade relative to the hub. If we cut the blade on a line extending through the center line of the prop, we can see the rake angle. Some props have a large amount of rake to lift the bow of the boat. When you trim the engine out, the engine creates a downward force which brings the bow of the boat up. These high-rake bow-lifting props are designed for applications where the engine is mounted high on the transom, with the prop surfacing or running partially out of the water. High-rake propellers grip the water well, with very little slip, which is helpful in rough water. But they can also make it more difficult for the engine to build RPM quickly on acceleration. Many high-performance props are designed to ventilate at slow speeds. This allows the engine to build up RPM and horsepower, getting the boat on plane and up to speed faster. Some of these props have holes drilled through the outer exhaust hub to allow exhaust gases to ventilate the blade area. At higher speeds, the water rushing past the hub seals off the vent holes, preventing them from ventilating the blades. Other props direct the exhaust gases over and through the hub. This provides more ventilation on acceleration than a through-hub design. This style of prop can be helpful on very heavy bass boats or in situations where a performance hull is powered by less than its maximum allowable horsepower. Many racing props use an over-the-hub exhaust design. All the exhaust gases escape around the prop hub, ventilating the prop on takeoff. The number of blades on a prop represents a compromise between top speed, acceleration, fuel efficiency, slip, and drivability. Theoretically, the fewer blades a prop has, the more efficient it will be at high speed. But props with more blades usually run smoother and slip less. For most applications, 3 blades is the best all-around choice. Some props have 4 or more blades for increased blade surface area. These may be necessary for bow-heavy boats, hard-to-plane or heavy hulls, or for running in rough water. Extra blades hold the water better, and they slip less on hard turns. Increased blade area can also improve fuel economy in the cruise range. The material used to make a prop affects its design and application. Aluminum propellers are less expensive than stainless steel and have reasonable durability. Stainless steel is 5 times stronger than aluminum and enjoys a performance advantage too. The extra strength permits thinner blades, so they move through the water more easily. Stainless steel blades deflect less under load, holding their pitch more accurately. Large outboard gear cases are available in standard and counter-rotation. Using a counter-rotation model on a twin-engine boat reduces the steering torque and improves the ability to track straight. Typically, the counter-rotator is on the port side, due to the dynamics created by the prop spinning. You can identify a counter-rotation gear case by the letters CR stamped on the end of the propeller shaft. The V6 line of stainless steel props feature innovative TBX hubs. This system employs a brass sleeve over the prop shaft and a separate plastic bushing between the sleeve and prop. It uses a conventional thrust washer in front and standard retention hardware in back. TBX hubs have numerous advantages over rubber hubs. The plastic bushing can handle higher loads, and it's better at tolerating the higher exhaust temperatures of low-emission engines. The smaller bushing increases the exhaust area through the hub, reducing back pressure. The alignment of the prop is more precise, which reduces vibration and wear on drivetrain components. The plastic bushing is designed to deform upon impact to absorb energy and still drive the propeller. This boater made it home without problems. The boater can replace the bushing if it's damaged. Unlike competitive hubs, the brass sleeve runs the full length of the bushing, reducing the chances of shearing under heavy load. Finally, never forget that no matter how carefully a prop is designed, it won't do the job if it's damaged. Props that are damaged by hitting rocks or other underwater objects should be repaired or replaced immediately, even if it's just some minor nicks on the leading edge or wear in the cup area. It can have a dramatic impact on the boat's performance, even causing engine damage. Props which are severely damaged, such as this one, should not be run at all. They can tear up a gear case in a hurry. Encourage your customers to carry a spare prop and hardware. If they hit something, it just might save the day. You may want to advise your customer to carry a spare that's one size lower in pitch than the optimum light load prop, because this makes the boat more adaptable to other uses. If your customer will be skiing with the kids or carrying a maximum load, they can improve the boat's performance by installing the lower pitch spare. Evinrude is constantly developing new props to provide the best choice for different boat and engine combinations, and we will review the current lineup. More props may be available since this DVD was released. Refer to the Parts and Accessories catalog for up-to-date information on our propeller lineup. Finding the right style prop for a given boat and engine combination is often a matter of trial and error. There are too many variables to make ironclad recommendations. The hull design, boat weight, load distribution, the engine's running characteristics, and how and where the boat will be used will all influence the propeller choice. The following recommendations may help, and you may also find performance reports for your boat or a similar model. The boat's manufacturer may also be able to offer recommendations. Aluminum props offer good performance at a low cost for many applications. Stainless steel props are more expensive than aluminum, but they're more durable, hold their pitch better under load, and their thinner blades offer better performance. Rake 2 props are designed for maximum bow lift and speed. They're a good choice for bass boats and high-performance boats. Rebel props are designed for great fuel economy and improved mid-range and top-end performance, particularly for offshore boats, large runabouts, and even large pontoon boats. Viper props provide good acceleration and top end. They're a good choice for recreational boats, from runabouts and cruisers to deck boats. Renegade 4-blade props are designed for heavily loaded bass boats and rough water. They help reduce steering torque feedback and hold better in tight turns. Cyclone 4-blade props stay hooked up in big water. They're a good choice for heavier and twin-engine boats, as well as runabouts that need transom lift. Rogue 4-blade props for the 40 through 115 horsepower engines get the boat on plane fast and maintain their bite in rough water. They work very well on flats boats and runabouts. Once you decide which style propeller to use, you must determine the proper pitch for the boat and engine combination. We'll cover this procedure later. Use the propeller selection guide or the boat builder's recommendation only as a starting point. An on-the-water test is the only way to be sure the correct propeller is installed. The owner's packet includes all the necessary propeller installation hardware. Some props may include their own hardware. Refer to the procedure in the operator's guide to install the propeller. Lubricate the prop shaft with triple guard grease. This is important to ensure the prop can be removed later. Be sure to position and orient all washers and spacers correctly. Tighten the nut to the specified torque. Use a block of wood to prevent the prop from turning. Be sure to secure the nut with the retainer and cotter pin. Make sure you wear a good personal flotation device when test running the boat. Always remember to connect the safety lanyard. Install any drain plugs. Launch the boat. Accurate tachometer readings are essential. Use an I-command gauge or the diagnostic software. If the boat has a traditional tachometer, compare the readings with the diagnostic software. Head to a safe area for a high-speed run. Accelerate to full throttle and check the engine RPM. The propeller should allow the engine to run near the midpoint of the recommended full throttle RPM operating range with a normal load in the boat. If you have less than the normal load, for instance, less people or gear than the customer will have, or if you're testing on a cool day, the outboard should run near the top of the RPM range. The outboard will produce less power on a hot, humid day because the air isn't as dense. Accelerate the boat onto plane several times. Check performance at various angle adjusting rod positions or power trim positions. To find the optimum trim position, trim the engine up until the RPM increases with no corresponding increase in speed. Then trim down slightly. You may need to try different props to achieve the optimum engine speed at full throttle. If the RPM is too high, try a higher pitch prop. If it's too low, try a lower pitch prop. For best results, you should try to achieve the engine's optimum propping point, which is a narrower RPM band than the wide-open throttle range. You can find a "Hey Ole, What's New" newsletter on DealerPort that will provide the optimum propping point for the engine year and model you're working on.